Okay, welcome again everyone. Today we will start with a summary of the Poisson process and solve a longish problem basically. So let's remember, first of all, a Poisson process is a counting process, right? That takes integer values, essentially increases one by one. Because the probability of having two or more arrivals at the same time is negligible. So a Poisson process, let me say, at rate lambda is an integer valued process n of t, right? N of t, let's define it for positive time, such that the probability that n of t is equal to k, meaning the number of arrivals by time t is equal to k, is given by lambda t to the k e to the minus lambda t divided by k factorial. That is the Poisson PMF for values of k 0, 1, 2 up to infinity. Okay, positive, non-negative integer values. It has the independent increments, also has the independent increments property, right? What does that mean? The difference n of t2 minus n of t1, meaning the number of arrivals in t1 up to t2, is independent of n of t4 minus n of t3, where t3 to t4 is a non-overlapping interval with t1 to t2. So this is t1, t2, this is t3, t4, okay? And it also has the stationary increments property, stationary increments. What does that mean? Basically, n of t2 minus n of t1 has the same distribution as n of t2 plus tau minus n of t1 plus tau, so for any tau. Okay, so basically it doesn't matter where the interval is, right? It just depends, the distribution of the number of arrival depends only on the size of the time interval. Right. Now, as a consequence of this definition, and you remember that we had two alternative definitions to this, but this is a complete definition in itself, and we can write as a consequence of this definition that the xi's, the inter-arrival intervals, are IID exponential with rate lambda. Okay. And as a consequence of this, if you consider the kth arrival time, the time of the kth event, I can represent this, of course, in terms of the summation of the inter-arrival intervals up to k. What is the distribution of Sk? Sum of k independent exponentials of rate lambda. And we show that this has the Erlang distribution. Erlang of order k, parameter lambda. What is the Erlang distribution? So let's just try to write the PDF. the Erlang distribution of order 1 is identical to the exponential distribution. Okay, it reduces to the exponential distribution, k equals 1. So remember, the exponential PDF is like lambda e to the minus lambda x. Now, in general, when we turn it to Erlang of order k, this lambda is going to take a to the power k. And I'm going to have k minus 1 factorial here, and k minus 1 as a multiplier, maybe. Let me see. X to the k minus 1 as a multiplier. X to the k minus 1. Am I right? Yes. That is x greater or equal to 0, of course. Okay, so that's that. What else? As a consequence of the exponential interarrivals, we have the fresh start property. And that is very useful when we're analyzing the Poisson process or models based on the Poisson process, because whenever you observe, when you start observing the Poisson process, it's as if you're observing from time t equals 0. What else? As a consequence of the same property, we have the residual life, residual time until the next arrival being exponential with rate lambda as a consequence of the memorylessness of the exponential. Furthermore, due to the same reason, the last arrival going backwards in time, the time to the last arrival in the past is also exponential, which implies the reversibility of the process. What else did we study? We talked about splitting and merging Poisson processes. So let's talk about the splitting result. When you take a Poisson process at rate lambda and take every arrival and independently send it to one process with probability p and another process with probability 1 minus p, and do this independently for every arrival. So you split it into two. We proved that the resulting processes are also Poisson processes, and they're independent. Their rates are lambda p and lambda 1 minus p. Right? And we will use this in the example that we'll solve today. How about the merging result? The merging result, it's the opposite. When you take k independent Poisson processes with rates lambda 1, lambda 2, lambda k, okay, and merge their arrivals and form one process, the resulting process is Poisson at rate what? Sum of the lambdas, I from 1 to k. And we proved this also. Okay, so that's essentially a quick review of the definition and properties of the Poisson process. Now, let's consider a problem that will allow us to exercise these properties. Here's the problem. Starting at t equals 0, buses depart from the METU campus according to a Poisson process of rate 0.2 buses per minute. So what is the mean time between buses? Huh? 5 minutes. Yeah, right. Each bus is independently assigned to go to Kızılay or to Ulus with probabilities 5/6 and 1/6 respectively. Oh, does this remind you something that we just reviewed? Splitting, right. Each bus is independently chosen to go to Kızılay or to Ulus. Okay. starting at t equals 0, people arrive at the bus stop according to a Poisson process of rate 1.8 people per minute. Okay, maybe this is a little bit faint. If I play with those lights over here, it might help. You think? Do you see this faintly? Let me try to lower the lights over there. Is this better? Okay. So, people arrive at a rate of 1.8 person per minute. Okay, so, and that's also a Poisson process independently of the bus arrival process. What can you say about like how many people per bus on average? 9 people per bus on average. And does it, like, when you think about the bus arrivals and the people together, when you combine them as arrivals, events, what do we have? If you record an event whenever a bus arrives or a person arrives, then you have events occurring at rate what? 2, right. 0.2 plus 1.8. And that merged process of events is a Poisson process at rate 2. Okay, now we're really understanding this model. Now people get on the first bus that comes. So if you're a person, you get to the bus stop, you're waiting there, you take the first bus and leave. You don't care whether it's to Ulus or Kızılay, you just want to get out of here. Okay? So, first question. I arrive at the bus stop and the bus just left as I was arriving. So I just missed it. How long do I expect to wait? 5 minutes, exactly an expected inter-arrival time. You see that? Let's in fact draw a picture. I'm just going to erase this. That's part A. So these are the bus arrivals. I happened to arrive exactly as this bus was leaving. And bus departures, I'm sorry, these are bus departures. And as I was leaving, this bus departed, so I'm going to wait for this inter-arrival time between 2 bus departure events. So the expectation of that thing, of course, is 1 over 0.2, which is 5 minutes. All right. B. I arrive at random. How much do I expect to wait? Now this is different. What's the difference of this? Same picture, but my arrival time is not coinciding with a bus departure. I arrive at a random time. How much do I expect to wait? I wait for a residual time, right, to the next bus event. What is the expectation of a residual time? By what we reviewed, the residual time by the memorylessness of the exponential also is equal to, right, the expectation of x, which is 5 minutes. Okay, no problem there. Now, what is the probability that the first bus I see is going to Ulus? I arrive here and I'm going to see the first bus that departs after I arrive. What is the probability it is to Ulus? Exactly, because every bus is to Ulus with probability 1 over 6 independently of when I arrive and what happens about, how much time passes, etc. So that probability equals 1 over 6. All right, let's go on to part C of the problem. It says, compute the probability that exactly 5 buses depart in the first hour. Exactly 5 buses depart in the first hour. This is related to the distribution of n of t, where t is 5, right? So the probability that n of, like, let's think in terms of minutes, right? N of 60 minutes equals 5. What is this? Lambda times t. Lambda is 0.2, right? 0.2 times 60 is 12. 12 to the 5, e to the minus 12 over 5 factorial. Any problem with that? Okay, now how about this? Compute the probability that at least 5 buses depart in a 1 hour interval. Does it matter if it's the first hour or any 1 hour interval? No. By the stationary increments property. Now, at least 5 buses departing in 1 hour. How do we do that? 1 minus 4 or less. Right. So this is the probability that n of 60 is bigger or equal to 5. But bigger or equal to 5 would require infinite summation. Instead, we could subtract from 1 the probability that n of 60 is less than 5 or less than or equal to 4. Which is 1 minus the summation kmi from, like, or k from 0 to 4, 12 to the k, e to the minus 12 over k factorial. Any questions so far? All right, let's look at part D. What is the probability that among the first 5 bus departures, 3 go to Ulus? Now, this has nothing to do with the Poisson process, right? It is a Bernoulli trial situation. Every bus departure is to Ulus with probability 1 over 6. So what is the probability among the first 5? 3 are, among the first 5 trials, 3 are success, for example. What is that probability? It's a binomial probability, right? Right, so 5 choose 3, 1 over 6 to the 3, 5 over 6 to the 2. Also compute the probability that the 5th bus departure is the 3rd bus departure to Ulus. Now that's different. What do you do in that case? So you look at the bus departures. Some are to Ulus, some of them are to Kızılay. 1, 2, 3, 4, 5. What is the probability that the 5th bus departure, is this one, is the 3rd to Ulus? This is an example. So now we don't only want 3 Ulus among the first 5 buses, but we want something stronger than that. We want the last one to be 2 Ulus. So
2 Ulus in first 4.
Exactly. Among the first 4, we want 2 to be Ulus, and then the fifth is also going to Ulus. Okay, very nice. So the probability there is 4 choose 2, 1 over 6 to the 2, 5 over 6 to the 2 multiplied by 1 over 6. Any questions? Question? No? All right. Good. So let's go to part E. All right. Find the probability mass function and the expectation of n, which is the number of people getting on a bus. So n is the number of people getting on a bus. It's a random variable. What do you think? Maybe this is a little slightly more involved because we haven't really been explicitly given this process of people and buses, the combination. But we made the observation that as the people arrivals and bus departures are both Poisson process, they're independent. When we merge them, the result is a Poisson process. And in the merge process, every arrival is from, every event is a people arrival with probability what? People are 9 times as likely as buses. So every arrival is a person with probability 9 over 10 and bus with probability 1 over 10. Right. So then, number of people getting on a bus. What's going on? These are buses and these are people. The number of people getting on a bus is going to be the number of people arriving between 2 buses. The expectation is sort of easy, maybe. The expectation should be 9. But how do we find the PMF? It's related to the second part of part D. It's related to this. The event that n is equal to k is the event that k people arrive before the first bus. Or why do I say first bus? Because I'm starting counting from here. And due to the fresh start property, the first bus after this point in time is like the first bus. I mean, so I'm looking for the probability that the k plus 1th arrival in the joint process is the first bus arrival, right? So n equals k means k people followed by a bus. Or among the first, same thing said differently, among the first k minus 1, I'm sorry, first k plus 1 arrivals, the first k are people. And the kth, k plus 1th, is a bus. Same thing. The k plus 1th arrival is the first bus arrival. Same thing. So the probability that n equals k then should be what? K plus 1 choose 1 No. Wait. Among the first k plus 1 arrivals, so among the first k plus 1 arrivals, the first k are people and the kth is a bus, right? Out of the first k arrivals, there's no bus, so k choose 0 if you want. 1 over 10 to the 0, 9 over 10 to the k, followed by a bus, because the k plus 1 should be a bus. That's 1 over 10. But that's a long way to just write down a simple probability. K people followed by a bus. The probability of that happening is 9 over 10 to the k times 1 over 10. Okay, that's the result. Yes, please.
I feel like we should have the zeroth arrival a bus so that we don't have any other people waiting already.
But I'm starting from this instant when the last bus left. I know that at this point the bus stop is clear. And when I start here, I start fresh, because even if there's an arrival, this is an arrival instant, the Poisson process starts fresh at that point.
But in order to guarantee that no people were waiting, shouldn't we like multiply it with 1 over 10 too? Or maybe I just don't understand.
I don't see the reasoning.
Because we shouldn't have any other people waiting on
Mm-hmm.
the bus.
Right.
Waiting on the stop, so we should have a bus arrival before any people arriving.
Right. So the number of people getting on a bus are exactly the people who arrived at the bus stop after the last departure. Right? This is the last departure. Right? Now there can be 0 people. Maybe that's why you're confused. It is possible. So this is the last departure. It is possible that I have another bus departure before anybody comes. And that's possible. Probability that k equals 0. So this is true for k bigger than or equal to 0. If k, so the probability that n is 0 will be plug in 0 there, 1 over 10. So a bus may come before anybody arrives. Or one person can arrive and then a bus. Or 2 people, etc. Mm-hmm. Yeah. So that's all covered here. Any other questions? All right, so now question is, did we find the expectation? We should compute the expectation. Clearly, it is going to be, let's see. Wait. What is the expectation here? Is it 10 or is it 9? Now, is this a geometric distribution with parameter 1 over 10? Not really, because it's 1 less than the geometric distribution. This counts the number of failures before the first success, if you will. If the geometric distribution is the number of attempts up to and including the first success in a sequence of Bernoulli trials, this is the number of attempts up to but not including the first success. right? So if you compute here the expectation of n, it is summation k from 0 to infinity 9 over 10 to the k times 1 over 10. That's not going to be 10. What is it going to be? So it's 1 over 10 times 1 over 1 minus 9 over 10, right? And that is, did I do this right? One over 10 times 10. Oh, I'm sorry. I need to put here k. Right. Right? And the result is going to be 9. If I was summing from k equals 1, I would be getting 10. Right. Or do you want to do this summation? Let's just do this summation. Shall we? Maybe let's just skip it. Okay. So, if I show up at the bus stop at a random time, what is the expected number of people on my bus? Now I am showing up at a random time just like this. So I can reuse this figure. Let's call this part F. Part F, I show up at a random time. What is the number of people on my bus? So the number of people on my bus is the sum of the number of people who arrive after me and before the next bus departure, and the number of people who were waiting when I arrived at the stop. Okay, plus me, right? So, what is the expected number of people arriving after me before the first bus departure? I just computed it, right? It's 9 because of the fresh start property. The residual life has the same distribution as any inter-arrival time. How about the number of people who were waiting when I came? Reversibility of the Poisson process tells me that that number also has the same distribution. So the expected number on the bus, number of people on the bus, should then be 9 plus 9 plus 1, because I'm also there, 19. What do you think? How many people are there on an average bus? Huh? 9. How many people are there on the bus that I observe when I arrive randomly? 19. What is the problem?
Isn't that paradox?
Yes. So that goes back to the random arrival paradox. When you arrive at random, you are your likelihood of sampling a large interval, inter-arrival interval, is larger. That's why this occurs. If we averaged the number of passengers on each bus, if we averaged this over buses, we would be finding 9. But if we average by random arrival, we're going to sample more crowded buses. Okay. I hope that's okay. If not, just ask me. I mean, I'm sure at this point some of you must have questions on your mind, and just, feel free.
Hocam,
Yes, please.
ile ilgili bir maddesinde arkadaşımızın sorduğu soruya geliyor da bu fresh start eğer arrival'ımız hani bir insansa da fresh start olacak. Dolayısıyla başka bir bölümü neden yaparız? Tamam. Hani ilk arrival'dan sonra fresh start diyoruz, tamam, sonra da probability'miz sağdaki gibi olacak. Ama ilk arrival'ımız insansa da yine fresh start olacak. Yani ilk arrival'ın da otobüs olduğunu
I see.
etmemiz gerekmiyor mu?
Now, what am I trying to find? I'm trying to find the number of all the people getting on a bus. What is the probability that this number is equal to k? So I need to count everybody getting on the bus. If I start counting with the first arrival of a person, then I would be counting 1 plus all the rest of the people, right? Yes. I can do that. That would be 1 plus the rest of the people getting on the bus, and that would give me something bigger than 9. That's your question?
No,
yeah.
The zero arrival is what I'm actually concerned about.
Let's first, maybe that Semanur was
yes,
nodding,
yes,
I
yes.
think. So yeah, 1 plus 9 essentially. But then there is the case that there is 0 people arriving between 2 buses. So when you average those two, 1 over 10 times 0 plus 9 over 10 times 10, that gives us 9 again. That does not completely answer your question, right?
I'm not sure. I'm trying to process it. Maybe after I think about it.
You can ask again. Okay, the last part. I arrive at the bus stop and learn that within the half hour previous to my arrival, exactly 6 buses departed. Okay, within half hour, 6 buses departed. Is that normal? Like, is that something that is close to average rate of departures? Yeah, so because like there's 5 minutes between buses on average, so that's exactly the average situation. What is the probability that all of these 6 buses actually departed in the 6 minutes prior to my arrival? So now that is a non-typical situation, right? What is the probability all of the 6 departed in the last 10 minutes of that 30-minute interval? What do you think? Let's try to find out. The probability that there were 6 departures in, let's say 20 to 30, the interval, time interval 20 minutes to 30 minutes, given that there are 6 departures in the interval 0 to 30, right? I can always write this. It doesn't matter where the interval is, as long as it's a 30-minute interval. Okay, but I can also turn this around using definition of conditional probability or Bayes rule. Probability is 6 in 0 to 30, given 6 in 20 to 30, times the probability that there is 6 in 20 to 30, divided by the probability that there are 6 departures in 0 to 30. right? Okay. Now, what is this first term? Given that there are 6 departures in the interval from 20 to 30, this is 20 to 30, then it is guaranteed that there are 6 departures in the interval, bigger interval that includes that, right? So this is then 1. How about the probability of 6 departures in 20 to 30? That's a Poisson probability, right? So it's a 10-minute interval. Arrival rate is 0.2 arrivals per minute, right? So 0.2 times 10 is 2. So 2 to the 6 e to the minus 2 over 2 factorial, 6 factorial. Divided by what? 30 times 0.2, right, is 6. 6 to the 6 e to the minus 6 over 6 factorial. Am I missing something?
Are we talking about exactly 6 arrivals? If so,
Yeah.
is the first term really 1? Because if we have 6 arrivals in 20 to 30, maybe we have...
Ah, it's very nice. Thank you so much, Semanur. That is awesome. I was about to make a wrong calculation. That's very nice. Did you all see that? Sometimes in probability we write something down and that misleads us, and that's what happened right now. Given that I have 6 arrivals in 20 to 30, I'm guaranteed to have at least 6 in this bigger interval, but I can have more, right? So in order to have exactly 6 arrivals in the total interval, I need to have 0 arrivals here. Perfect, thank you. So this probability is then not 1. This probability is the probability that there are no arrivals in 0 to 20. Right? Times, let's compute it with the, let's multiply with this probability 6 in 20 to 30. That is 2 to the 6 e to the minus 2 over 2 factorial. And this denominator is 6 to the 6 e to the minus 6 over 6 factorial. Huh?
That's also 6 factorial and right.
Thank you. Fortunately, the 6 factorials cancel. And no arrivals. No arrivals in 0 to 20. Lambda times 20 is 4. Right? 4 to the 0 e to the minus 4 over 0 factorial, 2 to the 6 e to the minus 2 over what? 6 to the 6 e to the minus 6. So the exponential terms cancel, and it turns out we have 2 over 6 raised to the power 6. My choice of numbers were not the best in terms of understanding this. But instead of these numbers, if I went with variables, maybe it would be more illustrative. So how about I say, given that I have this interval of size t, and I take this portion tau. What is the probability that there are k arrivals in let's maybe suppose this is x, okay? K arrivals in x to t, given that there are k arrivals in 0 to t. Okay, by the same argument, I can write this as probability 0 arrivals. So 0 in 0 to x, okay, times the probability that there are k in x to t, divided by the probability that there is k in 0 to t. Okay? And that would be lambda x to the 0, e to the minus lambda x over 0 factorial, lambda t minus x to the k, e to the minus lambda t minus x over k factorial, divided by lambda t to the k, e to the minus lambda t over k factorial. What is the result? The exponential terms cancel again. The factorial terms cancel. And this is 1. I end up getting, oh, the lambdas cancel too, t minus x over t raised to the power k. Interesting. This is also that. This is 1 over 3 raised to the power 6. I insist that all 6 arrivals occur in the 1/3 of the interval. Meaning each arrival, so each arrival, it seems, has probability 1 over 3 of falling into that last 1/3 interval. And I insist that all arrivals fall into that. You see, this is the general case. In the general case, the portion of time here is t minus x. The proportion to the entire interval is t minus x over t. With that probability, it seems, each arrival is going to be falling into this interval. And what is the probability that all arrivals fall into that interval? T minus x over t raised to the power k. This hints that perhaps conditioned on a given number of arrivals k in an interval, those arrivals are uniformly distributed in that interval. I haven't proved it yet, but it is true. And we are going to use it in the next lecture in our analysis of shot noise. Okay, so see you next time.